Let's talk about telescoping series. So I'm going to do two examples in this video, and they're both using the instructions you see here. Determine if the series is convergent or divergent, and then if it's convergent, compute the sum. All right, so right away with telescoping series, this chunk of the directions here to compute the sum, that's a bit of a giveaway that it's either geometric or telescoping, because those are the only two types of series where we could compute the exact value of the sum. And certainly this example here and the one following it down here are not geometric. So they've got to be telescoping. More specifically, what makes a telescoping series what it is, we can kind of see evidence of in this first example where the formula for each term of the series has like two forms that are very similar. So like as you start adding in the n=1 term plus the n=2 term and so on, some pieces of this will start to cancel each other away. That's the actual telescoping. Right. So for these series, our approach is the following. Write out a few of the first handful of partial sums. So the first, the second, maybe the third partial sum, enough so that you can get a formula for the nth partial sum. For most series, that's incredibly difficult to do. For telescoping series, because of all the cancellation we get, this should be possible. And then for this series, the series itself is equal to the limit of that Sn formula. Okay, so let's jump into this first one. We have the sum from n=1 to infinity of e to the 1 over n minus e to the 1 over n plus 1. All right, so I'm going to write out a few partial sums for myself so that I can start to develop a formula for what the nth partial sum would be. So S1 is the sum of just the n=1 term. So that's e to the 1 over 1 minus e to the 1 over 2. I could certainly simplify this 1 over 1, but otherwise nothing else special happens. S2 is the sum of the first two terms of this series. So I'll have the n=1 term plus the n=2 term. And we start to see a little bit of the telescoping start to happen, minus e to the half plus e to the half. So really this is e to the 1 minus e to the 1/3. And this first one was e to the 1 minus e to the half. We're starting to see a pattern. These are e minus e to the something. I'll do one more partial sum. There's not really a certain amount of partial sums you have to do. You just want to be really sure of your Sn formula at the end. All right, S3 will be the sum of the first three terms. So I have the n=1 term plus the n=2 term plus the n=3 term. And we have even more telescoping starting to happen. So these two terms, just like before, cancel out, but now the 3's do as well. And we have e to the 1 minus e to the 1/4. Okay, so for me, this is enough to start to get a pattern for the arbitrary Sn. So for S1, we have e minus e to the 1 over 2. For S2, e minus e to the 1 over 3. And then finally for S3, e minus e to the 1 over 4. So they all have e minus. I'm going to drop that one exponent here. And then we have e to the 1 over. So when this subscript is 1, it's 2, and then 2 is 3. So I'm not going to say n, I'm going to say n plus 1. All right, so if I plug in a couple of n values and double check, this should match what I already have. So now my series, n=1 to infinity of all this, equals the limit as n approaches infinity of this partial sum formula. All right, so overall, I don't really know what this graph is doing, but if I zoom in on the 1 over n plus 1 situation, I know that part will go to 0. So my final limit will be e minus e to the 0, which is e minus 1. So because this came out to a number, we can also conclude that the series was convergent and equals E minus 1. All right, so that process should hold us every time, although the actual formula you get for Sn, of course, will change series to series. Let's look at a second example that has something a little extra going on in it. So this one, we're imagining you start with the sum. I switched it to k instead of n here. It doesn't really change anything. So the sum k equals 1 to infinity, negative 2 over k plus 1. So this is the type of series where like you may try a few things, and then if you want to see it as telescoping, you've got to do partial fractions. So this negative 2 over k times k plus 1, this actually is, if you break it up, a formula similar to this that will start to cancel itself. But it's not really in that form yet. So I've pre-done the work here. I just did some partial fractions, something over k plus 1. And I got my two numerator values. So I can take this series and rewrite it as a, which is negative 2 over k, plus b, which I got as positive 2 over k plus 1. Now I have these in the opposite order. This is 2 over k plus 1 minus 2 over k. It doesn't have to be written that way, but you may find it a little more obvious that it's telescoping if you switch it to subtraction. So now it's kind of hinting a little bit more at what it truly is, a telescoping series. And so I can get started with the same process as the example above. Write out a few partial sums, start to see the telescoping happen, develop a formula for the nth partial sum, and then the limit of that formula is the sum of the series. Okay, so the first partial sum is just the very first term. So that's the k equals 1 term here. So that's 1 minus 2. I'm going to leave it in that form because I'm not really looking to compute. I'm looking to see a pattern. So I'll leave it like this. S2 is the sum of the first two terms. So I have the k equals 1 term plus the k equals 2 term. And I have a little bit of telescoping, 2 over 2 minus 2 over 2. So this comes out to 2/3 minus 2 over 1. I'm writing it in that order just so that it kind of mimics the order of the first one. And then we'll have a similar situation for S3. I usually like to do about 3, but you do as many as you need to be sure. So we have the first term plus the second term plus the k equals 3 term. And a little more telescoping, so the 2 over 2's are still gone. Oops, that should have been a minus. That's why that didn't cancel. Okay, there we go. And then plus 2 over 3 minus 2 over 3 also cancels. So what's left is this 2 over 4 minus the 2 over 1 from the very beginning. Okay, so I have 1 minus 2, 2 over 3 minus 2, 2 over 4 minus 2. So I can start to put together, it's not S4, Sn. They all have 2 over something minus 2 over 1 minus 2 over 1 minus 2 over 1. So they're all minus 2. For 1, it's a 1 there. For 2, it's a 3 there. For 3, it's a 4. So I'm again going to say n plus 1. All right, so throw in a few n values, make sure it actually is cranking out the correct numbers. And then once again, our series. I'll use its original form, but it doesn't really matter which form I take. This will be equal to the limit as n approaches infinity of the Sn formula. So in this case, this part of it goes to 0. So we have 0 minus 2 is negative 2. All right, so the series computes exactly to that value. And because this limit exists, the series once again is convergent. The only difference that you would see if a telescoping series were going to come out divergent, which is possible, all of this would go the same way. It would just be in this step right here when you're computing the limit. It would be some sort of does not exist limit where numbers are getting too big or they're oscillating, something like that. But they all have the same approach that we've done here.